Hello everyone, I'm Jiaqi Chen from University of Wisconsin-Madison. Today I will give the presentation of our research on the data-driven piecewise linearization for distribution three-phase stochastic power flow. In recent years, the integration of distributed generations in distribution networks is increasing rapidly. The uncertainties of the digits, such as the wind powers and the PVs, may significantly undermine the reliability and the security of the distribution networks. Therefore, we need to use the stochastic approaches rather than using the traditional deterministic approach to analyze the system. Moreover, in the analysis, we need to consider the correlation of the random variables and the three-phase unbalanced nature of the distribution system. The three-phase stochastic power flow is an important tool to analyze the distribution system. Typically, it can be classified into three types. For the analytical methods and approximate methods, they will be complicated when the correlation and the three-phase characteristics are considered. Therefore, in our research, we use the Monte Carlo method, which belongs to the simulation methods, to calculate the three-phase stochastic power flow. But the Monte Carlo method requires numerous calculations of three-phase nonlinear AC power flow, so its computation burden is very high. To solve this issue, we proposed to use the power flow linearization approach to linearize the power flow to speed up the calculation process. In general, the power flow linearization approach can be classified into two types: the model-based linearization approach and the data-driven linearized approach. For the model-based linearization approach, it has many limitations. We need to know the system's topology and the accurate system parameters in this approach. But sometimes we don't know the system's topology and the system's accurate parameters. Moreover, even though we know the topology and the accurate system's parameter, the approximation of a certain term for the power flow equations will also involve errors. For example, there are some assumptions that the voltage magnitude should be 1, but it will not be true for all operational conditions in distribution systems. With the increasing amount of measurement devices, the data-driven linearization approach has become a promising way to solve above issues. We can directly regress the target function from the data points, so we don't need to consider the inner mechanism of the approximation. And the training data for the data-driven approach can be from two sources. Firstly, the training data can be from the measurement devices. In this scenario, we don't need to know the system's topology and the accurate system parameters. And from the discussion later, we have shown that this approach is applicable when the system is fully or partially measured. And another source for the training data is from the AC power flow calculation. In this scenario, we'll assume we know the system's topology and accurate system parameters. We generate the training data from the accurate AC power flow model. In this scenario, because we directly regress from the data point, we don't need the approximation like in the model-based one. So it will be more accurate than the model-based approach. And because we obtained the linear power flow model, it will be faster than the nonlinear AC power flow calculation process. And the questions next is how to make our approach more accurate. From this point, we can find if the relationships of the data points are nonlinear, Using one straight line to approximate the relationship will involve errors. To improve the accuracy, we proposed to use the piecewise linear function in red to approximate the relationship. And the questions next are how to find the relationship, the regression coefficients W for each partition, and how to determine the class center mu for each partition. To solve this problem, we proposed an improved K-plane regression algorithm. Next, I will introduce the detail of this algorithm. For K piecewise affine function in each partition, we have the affine function in this form, and our arrow function is in this form. The objective of our algorithm is to minimize the arrow function, while let the hyperplane Wx be close to our target y, as well as let the point x be close to the class center mu. And to point out that because in the data-driven power flow linearization approach, collinearity exists among the training data. So here we add a penalty term to solve the issues caused by the data collinearity. And this error function can be decreased through the following iteration. We have the training data x and y as the input variable. And firstly, we initialize the parameters. We initialize the coefficient W, the class center mu, and the class set S. And then we do the regression process. In each cluster, we use the two equations to calculate the coefficients W and the class center mu. After that, we cluster all the data into new cluster set S with this equation. And then we repeat the process until there is no update for the cluster set. In the end, we obtain the piecewise linear function fx and the class center mu. And next, we apply this improved K-plane regression algorithm to calculate the stochastic power flow. The three-phase stochastic power flow calculation approach contains two processes, the offline training process and the online application process. For the offline training process, we use the improved K-plane regression algorithm, which we just proposed to train the three-phase piecewise linear power flow model. In this model, we find the relationship between the power injection X and the branch power flow and the voltage magnitude Y. And then we apply this LPF model to the online application to calculate the stochastic power flow. The online application process includes four steps. Firstly, we generate the data samples for the Monte-Carlo method from a certain distribution. Then we determine the partition of each data sample using the class center mu to determine that we have obtained from the training process. And next, for each data sample, we use the specific LPF model which we have trained from the training process to calculate the power flow. In the end, we aggregate all data samples to obtain the three-phase stochastic power flow. Because in our approach, we use a linear form of the power flow and the piecewise form of the power flow, and the model is three-phased, our approach can calculate the stochastic power flow efficiently and accurately, as well as considering the three-phase unbalanced nature of the system. Because we use the improved K-plane regression algorithm, we can also solve the issues caused by the data collinearity. Next, we test our approach in two aspects. Firstly, we test the proposed LPF model to calculate the power flow. This table shows the max and mean errors of the power flow calculation results without data collinearity. From this table, we can find the max and mean errors of our proposed approach much smaller than other power flow linearization approaches. And then we test the accuracy of our approach under data collinearity. We will assume the data collinearity exists in the training data, and from this figure and this table, we can find in the test case the errors of our proposed piecewise LPF model are much smaller than the other piecewise and then other power flow linearization approaches, which means our approach is more accurate to calculate the power flow. And next, we analyze the performance of our proposed approach with partial measurement data. We assume in the training process, the power injections for all nodes is measured, but we only have the measurement data of the voltage magnitude of phase A of node 2 and node 11, 116. And this table shows the errors with fully and partially measurement data. We can find all the max and mean errors are the same for node 2 and node 116, which means that even though the system is partially measured, our proposed approach is able to derive a partial piecewise LPF model for the measured branches or nodes. But for the model-based approaches, we can't obtain the partial piecewise LPF model. This is the benefit of our approach. And then we test our approach on the stochastic power flow calculation. These figures are the probability distribution functions of the stochastic power flow calculation result. Here we use the back-forward swap BFS algorithm as the benchmark. They are treated as the accurate result for the stochastic power flow. And from these table figures, we can find our proposed piecewise approach almost overlaps with the result of the BFS result, which means our approach is accurate enough to calculate the three-phase stochastic power flow in distribution systems. And in the end, we compare the computation time of our results with other methods. From this table, we can find for the piecewise linear approach, the computation time is much smaller than the BFS approach, which means our proposed approach is efficient enough to calculate the stochastic power flow, especially compared with the accurate method, the BFS method. In conclusion, we propose an improved Kaplan regression algorithm to derive a new data-driven piecewise linear approximation for the three-phase power flow, considering the collinearity of the data. And we devise a stochastic power flow calculation process based on the Monte method with the proposed piecewise LPF model. And the proposed approach is computationally efficient while maintaining very high precision and considering the three-phase unbalanced characteristics of the distribution systems. And we have discussed that the proposed method can be utilized in a setting with partial measurement data, which is the benefit of our approach compared with the model-based one. This is the end of my presentation. Thank you for listening.